Welcome you all in the fluid mechanics lecture. Today topic is continuity equation. Continuity equation is a conservation of mass. So here we are first taking the non-conservation form, that is the Lagrangian approach. So we know in a fluid mechanics there are the two approaches. One is Lagrangian, other is Eulerian approach. So in a non-conservative form, conservation form, this is the Lagrangian approach. In a Lagrangian approach, here this is a infinitesimal fluid element which is moving in the direction of flow. So this is the flow field. So here it is a very small fluid element. So we know the rate of change of mass because the we assume the mass of this element is constant. So the rate of change and of mass, this is delta m is constant. So the rate of change is equal to 0. So we can write delta m rho density into volume. So and we differentiate it with respect in by parts. So we differentiate first term, second term take as a constant, and plus first term take as a constant and differentiate in a second part. This is equal to 0. This is equation 1, and we differentiate we divide this equation 1 with delta v. So we will get this one. So we know from the definition of divergence of velocity in a last lecture. So this value equals to divergence of velocity. So we can write in place of this term divergence this term. So we know this is called continuity equation in a non-conservation form. So here if we see the rate of change of density is balanced by the divergence of velocity. Here this is the rate of change of density. This is balanced by the divergence of velocity. Continuity equation in a conservation form. Conservation form, this is also called the Eulerian approach. In a Eulerian approach, we consider here finite control volume in a flow field. Here this is the flow field, and here this is the finite control volume. So here we know the net mass flow rate, means mass will enter through these surfaces, right? This is the cuboid. So through this cuboid, surface of this cuboid, mass will enter here from this, and so the net mass coming from the surfaces, this is equals to the rate of change of mass within the control volume, which will equals to the rate of change of mass within the control volume. So we can write it the this is the velocity of the fluid, and this is the cross-sectional area. So this become the volume flow rate. In this is multiplied by the density. This become mass flow rate. So mass flow rate we generally represent m dot. So this is mass flow rate coming through the control surface. This is equals to the rate of change of mass within the control volume. So I am writing it CV, control volume. So this is rho, this is density, and this is the volume. So mass into volume, this become the mass, and this is the rate. So this become mass flow rate. So this is also mass flow rate. But here this is the negative sign. This is very important. Why this negative sign? When, for example, here this is a tank, mass coming in M1, and mass flow rate this is M2, right? So when M1 is greater than M2, M1 is greater, so M1 minus M2 equals to the, so here what will happen if M1 value is higher, so the and M2 is less, so the mass initially, for example, it is here, So it will store here. So means change. So initially this one v1, so this become the negative. Initially initial minus final, or it will take final minus initial and final minus initial. So so this is negative, so this will positive. So one term will positive, other will negative, right? So this is the reason here. If this is increase, mass is increasing, so here within the control volume it will decrease, right? So this is the negative sign. So uh, so now we can write it, this term first here. We can write this term here first, and then then this one, then second term, right? And and here this is the uh, control surface convert into the control volume. We know the Gauss divergence theorem uh, to uh, to convert the control surface into the control volume, right? So this is the for the control volume. So we can write this one, and so then this one, and we take this integration outside within the control volume. So finally this is our uh, this is the continuity equation in a conservation form, right? Uh, and conservation form is, this is the Eulerian approach. Eulerian. So Eulerian. Okay. So please like my channel, like, share, and subscribe my channel. Please like, share, and subscribe. If you have any doubt, any question, please write it in the comment section. So I will try to answer your question. Thank you very much.